Hello everyone, this is Team 2, my name is Julia, and my teammates are Peter, Alexander, William, Zonda, and Joseph. This is our final presentation for ME 452 and ISD 528. We decide to analyze and redesign an electric kettle. Electric kettles are commonly used to quick boil water for a variety of culinary applications. The main features of the kettle are its ability to maintain hot water temperature and disconnect from heating element for efficient pouring. They are really cheap and convenient to everyone. That's the reason why our primary customer group are families in residential settings who use it in everyday base to prepare hot beverages or food. The secondary customer are employees in communal office settings who attend to make their own cups of coffee or tea.
Moving into the functional analysis of the electric kettle, this fast diagram remains the same as the one as the interim presentation except for one component, namely, avoid electrocution was added to stem from assured dependability. Next, we have our function component mapping matrix. All functions from the aforementioned fast diagram are linked to each part. The diagram on the left-hand side calls out each part numbered 1 through 15. Here, the diagram is omitted so all 15 parts can be shown on a single slide. Next, we have the function comparison between the two product families. Each function is again directly from the fast diagram. The only change from the interim presentation is that avoid electrocution has been added to the left-hand column, denoting that it is a function that is the same for both customer groups. Here we have the part comparison between customer groups. This table remains the same from the interim presentation. Only the kettle body is a module, as it is a different size for each customer group. As just mentioned, the kettle body varies in size according to the customer group. Here we have images of each kettle body. Specifically, the primary product variant contains 1.7 liters of water, as it is for household use, and the secondary product variant contains 2.3 liters of water, as it is for commercial use. Moving on, we depict common interfaces. First, the handle interface in Subassembly is the same between both product variants. In addition, the lid and base interfaces are the same between both product variants. Depicted here is the delayed differentiation assembly model. First, all components of the base subassembly are assembled as they are common between both product variants. Next, differentiation occurs via the attachment of the kettle body, as all subsequent parts must attach to this component.
This slide shows the design for manual assembly of our electric kettle, with a total assembly time being about 155 seconds and a theoretical minimum number of parts at 10, with a design efficiency of about 0.2. We identified that the screws in our design resulted in about half of our total assembly time and could be a source for design optimization. We identified a platform in our design that could be improved to improve our design efficiency through the elimination of fasteners. The picture on the left shows our initial design for our base and base lid. The picture on the right shows our redesign of our base and base lid with the elimination of fasteners and thus the elimination of fastener holes. The base would have an external male type extrusion for a snap fit, while the base lid would have an internal female type groove for a snap fit. The design guidelines that helped in this were DFAS 1, DFJ 1, and 3. We also found our kettle body module would be a source for design improvement through the elimination of fasteners. The picture on the left shows our initial design for the two parts, while the picture on the right shows our redesign. The redesign includes a locking port for the handle, the elimination of the fastener holes in the handle, and an extrusion locking into the kettle body. This slide shows our recalculated assembly time for our redesigned electric kettle. Our new assembly time is about 76 seconds, while our theoretical minimum number of parts stays the same at 10. Our new design efficiency is about 0.4, with a percent improvement of over 100%.
The selected platform subassembly for automated assembly enhancement are the parts involved with the base and electronic component module, namely the base lid, base electronic component housing, BS1363 plug, and screws, which are shown in this table. Estimating the original design's total assembly cost was achieved by summing each component's handling feeding costs and insertion costs. Due to the nature of automated assembly, most of the cost is associated with handling rather than insertion. Based on product volume, a desired feed rate of 6 parts per minute was chosen, and the product design for manufacturing and assembly tables were consulted to estimate orienting efficiency and relative handling costs. The original design yields a total assembly cost of about 10 cents. As seen in these original design figures, we noticed 3 areas that could be improved via design for assembly guidelines. The following changes were made to improve orienting efficiency and reduce relative handling costs. As we now show in the redesign, DFJ1 was utilized by removing the forwardmost screw connecting the base and base lid. This screw does not further secure the electronic component housing, and 3 securement points already exist between the base and base lid. Next, DFPI1 was utilized by adding chamfers to the insertion holes for all 3 remaining screws. Lastly, DFPH1 was utilized by increasing part symmetry of the electronic component housing. Currently, the upper part thickness of the outer shell is wider than the base, but by making the thickness uniform, it could be inserted in either Z-axis orientation. As shown in the redesign's product design for manufacturing and assembly table, making these improvements reduces total assembly cost to about 7 cents.
We then selected the manufacturing processes for the parts that we previously redesigned. These include the handle and base parts. We determined that these would be plastic parts. For the handle, it requires an interference fit, and the part itself is hollow with a 2 mm wall thickness. The mass is relatively low with a 0.1 kilogram weight, around a 0.1 mm tolerance, and the surface finish must simply be satisfactory for the user. We previously determined that the batch size would be 50,000 units. Thus, by comparing these processes, we selected injection molding. Similarly, for the base parts include snap fits. However, this part is a solid part and not a hollow part. However, this ended up giving us the same process as the handle, which is injection molding.
The design for manufacturing of handle, 4 screws were eliminated which were holding the handle and the kettle body together by creating handle futures via extrusion. Subsequently, the handle futures locked into a slot in the kettle body via an interference fit. The material cost increased by 25%, and the overall savings by replacing the screws were $0.52, as you can see in the table.
For redesigning the base, we eliminated 4 fasteners and added extruded material to join the male and female parts of the base via snap fit. Adding this extruded material increased our overall material cost by 31%, as well as increased the process and mold costs for the part. But eliminating the fasteners had a large impact on costs and reduced our overall cost per part by 61.5%.
For the design of product service system, our product is modularized, so we are encouraging users to utilize a free part replacement service while the product is under warranty. This will also incentivize continual interaction with customers and allow us to make potential future product offers. We plan to offer free return shipping within warranty of either platform base, platform handle, or the variant kettle body. Since they won't be returning the full assembly, the smaller weights of just the damaged module reduces shipping costs for us, as well as environmental waste for packaging and increased fossil fuel emission that we'd see with heavier transport loads. Once the module is received, we plan to salvage parts that are in near mint condition for future refurbished parts replacement. This is the key to our PSS. By using salvage parts, we are reducing the environmental impact by avoiding additional manufacturing. The following is an illustration of the cycle at work. All components besides the shorted fuse will be salvaged for future refurbished module builds. In the end, we return a prior built refurbished base electrical module to the customer who submitted the claim. The DFMA analysis and redesign was overall a successful endeavor. The redesign saw improvements in ease of assembly and decrease in costs. Some cons we saw with our product was the difficulty in accessing the base subassembly once it's been assembled in order to fix electrical components that may be damaged. The snap fit between the handle and kettle body is also possibly not as reliable as the original design. Some additional research could help us identify less energy-intensive materials to manufacture that still contain heat adequately. We would also like to redesign the electrical components housing arrangement into this base subassembly. If we would repeat the process, we would likely take part consolidation into account earlier in the design process and possibly merge the base and kettle body into one fixed subassembly.